Ken Ray, and here I'm gonna introduce to you about breadth first search algorithm on binary tree. So here is a simple question on lead code. So what is a binary tree? Binary tree means that for each root node, it has two children, a left children and a right children. And what's level order traversal? For example, we have a tree over here. The first level is 3. The second level is 9 and 20. The third level is 15 and 7. And here is the expected output of this question. We need to group each level together, and then we get all levels together and print them. Okay, and the first algorithm come to my mind is BFS algorithm. Here we have a simpler example. 1, 2, 3, 4, 5, 6. If we print them level by level, we print 1, 2, 3, and 4, 5, 6, right? And here is the pseudocode of a BFS. The essential data structure, if you know, it's a queue, right? So we use a queue to do the BFS iteratively. So first of all, we need to deck this queue and explore the current node. Then after we explore a current node, we need to get all these neighbors and put them on the queue. And we will continue visiting them later. This is kind of abstract. Let me help clarify this concept by walking you through an example. For example, for this tree, right? First of all, we visit the node 1. We will put this on the queue. In the queue, currently, we will only have one element, and the size of this queue is only 1. So we delete one element from this queue just one time. We delete 1, and we put 2 and 3, which are the children, the neighbor of 1, onto this queue, right? So now the queue has 2 and 3, and we already visit 1, and this is our result. And in the step 2, we have 2 and 3 on our queue. The size of this queue is 2. So we need to delete this queue for 2 times. First of all, we delete 2. And the neighbor of 2 is 4 and 5. Then we delete 3. The neighbor of 3 is 6. Because the node 3 does not have a right children, so the node 3 only has one neighbor node, which is its left children, node 6. And right now, we delete 2 nodes in this iteration, so we visited 2 and 3. In the last step, we had 4, 5, 6, and the size of this queue is 3. So we want to delete elements from the queue for 3 times. So we delete 4, 5, 6 each by each, and we have the result, 4, 5, 6. And eventually, we print 1 in a level, 2, 3 in a level, and 4, 5, 6 in a level. And this helps us solve this question, right? And over here is the complete code I just implemented. And we need to be aware that there might be a corner case over here. If our root is null, we have to return an empty list. And this is as shown at here as a corner case. And we should be really careful and pay attention to details when we are writing an algorithm, right? And here is the complete step of this algorithm. And also we need to be careful that we need to put the left node, the left children onto the queue before we put the right children onto the queue. This is because we are visiting this tree in order. We are visiting 1, and then we put 2 on the queue and 3 on the queue, right? Then the children of 2, 4, and 5 will put on the queue first, and 6 will put on later. So we have to make sure this order is maintained so we can get the correct result. So to analyze the time complexity of this algorithm, the time complexity would of course be O(n), right? Because from the pseudocode over here, we can see that each node is deleted from the queue 1 time. And each of them is offered on the queue for 1 time. So the total time complexity is O(n). This is the time complexity of BFS algorithm. and the space complexity of this algorithm would be how much? It would also be O(n), right? Because we used a queue to maintain this data structure. And in the worst case, the size of the queue might be the size of the tree, right? And we can ask n to be the number of nodes in the tree. Is this clear? Yeah, and this is my explanation about the BFS algorithm on a binary tree. If you have any other questions, you can ask me to clarify. And we can just run this code, and we can see this code is working as expected. Yeah, and thank you very much for watching this video.